Hi, my name is Rudy Coppola and I'm a graduate student at KAUST. I would like to present to you our research on road users classification using a commercial radar sensor. Our work is based on Infineon's position-to-go, frequency-modulated continuous wave radar. This module is equipped with a 24 GHz transceiver chip and a 32-bit microcontroller. One transmit and two receive integrated microstrip patch antennas are printed on the PCB. The classification of targets is performed on a two-frame basis. In one frame, 128 pulses are transmitted, each sweeping a band of 200 MHz over an up-chirp duration of 300 microseconds. The pulse repetition interval amounts to 500 microseconds. Hence, the acquisition time is 64 milliseconds. The frame repetition interval is 200 milliseconds. The device in this configuration achieves 75 centimeters of range resolution, 48 meters of maximum range, 0.01 meters per second of velocity resolution, and 6.2 meters per second of maximum velocity. 64 samples are extracted from each chirp and transformed via fast Fourier transform to locate the targets present in the scene. Static scatterers are suppressed via moving target indication filtering. The phase history of the remaining moving targets is sampled and transformed via fast Fourier transform to obtain the Doppler spectrum. We consider three different classes of targets: pedestrians, cyclists, and cars. Each class has a unique motion. When a human is walking, the Doppler spectrum's strongest component is due to the torso, approximately moving at a constant speed. However, other body parts as feet, knees, arms are also in motion relatively to the torso. They produce a microdoppler and are visible in the Doppler spectrum as several peaks. Similar arguments are also true for a cyclist. Since the arms are constrained on the bicycle handles, the dominant limbs in relative motion to the body are only the legs. A distinctive trait of a cyclist's Doppler spectrum is the presence of a widespread of weak frequencies imputable to the wheel's return signal. These frequencies theoretically correspond to velocities ranging from 0 meters per second at the bottom of the wheel to twice the cyclist's velocity at the top of the wheel. Lastly, cars' typical Doppler spectrum has a single strong peak at a frequency corresponding to the vehicle's speed. A weak return signal of the tire was observed. However, because the car's bumper typically covers part of it, the spread of frequencies is asymmetric with respect to the vehicle's speed. We extract the target location and a set of features from the Doppler spectrum, accounting for peak number, strength, distance, and distribution around the dominant frequency. The change of these features from frame to frame is also accounted. Notably, the absolute speed of the target is not considered. Although it can be an important parameter for classification when the radar is fixed on the ground, we wanted to create a classifier for a radar system that can be mounted on a vehicle and still perform the same. We use gradient-boosted trees for classification. Our dataset comprises over 1,600 Doppler spectra belonging to the three classes of targets moving in a radial direction relative to the sensor's field of view. The dataset is split for training and testing. We analyze the trade-off between accuracy and feature number. The model with the highest score after five-fold cross-validation is selected for testing. The results are visible in the following footage. For completeness, we extend our model to consider different directions of motion. For each class, we examined radial, diagonal, and perpendicular motion. We obtained the following results. Over 90% of accuracy is achieved when the target moves in the radial direction. The most challenging scenario occurs when a target moves in the perpendicular direction. We can see that the cyclist and the car are harder to distinguish. However, the pedestrian is still correctly classified in 84% of the cases.
In summary, we have presented you our model with the information based on 2 subsequent frames. With this approach, we have achieved 87% of accuracy for pedestrians, 80% of accuracy for cyclists, and 79% of accuracy for cars. So far, only the data of one receiver was used for the predictions. In the future, we plan to add multiple receivers to include important geometrical information, such as the width of an object. If you would like to know more, don't hesitate to get in touch. Thank you for your attention.